So next in our study of counting, we want to look at permutations, which just means how many different orders I can write different objects in. If I have the letters A and B, there are two permutations because I can write those letters in two orders, AB or BA. Alright, what about if I had three letters? How many different orders can I arrange those three letters in? So I can try to write them all out, or a more systematic way to get the possibilities is to use a tree diagram, which we talked about in the first video. So let's just do that. My first letter choice could be A or B or a C. If I choose A as the first letter, then I could have B and C as the second letter. B is the first, A and C is the second, C is the first, A and B is the second. And then for the third letter, I could have A, B, which would make my third letter C, or A, C, making my third letter B, and so on. And so I can see that I have 6 possibilities, just highlighting one possibility there. So I can see that I have 6 possibilities, and I could get that with the fundamental counting principle, because for the first category I can see that I have 3 possibilities. For each of the possibilities in the first letter, I have 2 for the second. And for the third letter, for each choice in the previous line, I have 1 choice for those. So 3 times 2 times 1 is 6. And 3 times 2 times 1, we have a special way to write that, and we write it as 3 factorial, as we call it. The exclamation mark is called a factorial sign, and by definition 3 factorial means 3 times 2 times 1. Okay, you don't have to get excited when you say 3 factorial. The explanation mark just means 3 times 2 times 1. Alright, so how many permutations do we have? We have 6. So then if we ask how many permutations of 4 letters are there, it probably makes sense if we just do this. We could again do a tree diagram, but there's 4 ways to choose the first letter, 3 ways to choose the second letter, 2 ways to choose the third, and 1 way to choose the fourth, which would be 4 factorial, and 4 times 3 times 2 times 1 is 24. And you can get the factorial on your calculator, by the way, by going to Math and then over to Probability, the 4th one over here. There it is right there, number 4. So you actually have to put the number in first. 4, Math, Probability, and it'll tell you that it's 24. Okay, in our next situation we have 5 letters. We know that if we took all 5 letters and wanted to know the number of permutations, that would be 5 factorial, but we're being asked something different here. Instead, we want to use all the letters to form permutations using 2 letters. So for example, if I use all 5 letters and just want to pick 2 of them at a time, DB would be one permutation, BD would be another permutation, AC would be another permutation, etc., etc. The question is, how many different 2-letter permutations can you make using all 5 letters? Alright? And we actually have a notation for what we're being asked here. We're being asked to take the 5 letters, and we want to know how many permutations there are of 2 letters at a time. And we say 5p2. Alright? So I could use a tree diagram just like I have before to work this out. And since we've done this a couple of times, we can probably just think this through in terms of, for the first letter, there'd be 5 different choices. For the second letter, there would be 4 different choices, and that would be it, since we're doing 2-letter combinations. So there'd be 20 permutations if I were to write them all out. Alright, in terms of a formulaic way to get this, we know that if we were using all 5 objects, that we would have 5 factorial ways of arranging all 5 letters. But since we can see from our calculation that we just want to have the 5 times the 4 as our answer when we're taking 2 of them at a time, what we're going to do is divide away the 3 times the 2 times the 1. Alright? In other words, 5 factorial divided by 3 factorial. This will cancel this and give us our answer of 5 times 4. Alright? Which suggests that when we're asked to do 5p2, the way we can do this with a formula is take 5 factorial and divide by the difference between the 5 and the 2 factorial. And that's 20. And again, on your calculator we have this button. If I want to enter 5p2, I will enter the 5, math, over to probability, number 2, 5 items taken 2 at a time. That's going to calculate 5 factorial divided by 5 minus 2 factorial, in other words 3 factorial, and there's my 20. So how many 3-letter permutations are there using all 5 letters? Well, that would just be 5p3, which by formula is going to be 5 factorial divided by 5 minus 3 factorial. So 5 factorial divided by 2 factorial. And you can go to your calculator to do this. 5 factorial is 120. 2 factorial is 2 times 1, 2. So there's 60 different permutations. And so just to generalize some of these major results that we have so far. An ordered arrangement of objects is what we call a permutation. And the number of permutations of n objects, if we take all n objects, we can get the number of permutations by going n factorial. And if we have n objects, but we're only going to take r of them at a time, then the number of permutations is npr. And the formula for that is n factorial divided by n minus r factorial. Okay, let's just see how this works with some real-life examples. You press the scramble button on your CD player, or I guess these questions are a little dated, maybe your MP3 player, and it plays permutations of songs on the CD. Let's suppose you have 5 songs. How many different orders can the songs be played in? How many permutations of the song are possible? So we're doing all 5 songs, so that's just 5 factorial. So there's 120 different ways, different orders that those 5 songs can be played in. By the way, if you said 5 permutations and I'm going to take all 5, these two things should be the same thing because they, intuitively mean the same thing when you say them. 5 things, pick all 5. If you use your formula, you're going to get 5 factorial divided by 5 minus 5 factorial, which is 5 factorial divided by 0 factorial, which is 120 over, and I haven't mentioned this yet, but 0 factorial by definition is 1. Okay? And so there's your 120. How many permutations using all the letters of the word compute? There's 7 letters, so 7 factorial, whatever that is, will give you the number of different orders. But if you were taking only 3 letters of that word, it would be 7p3, and you could compute 7 factorial over 7 minus 3, 4 factorial. So just as a final point on this video, just a little bit more on the factorial notation. So 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, etc. N factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down till we get to the n, 3 times 2 times 1. Okay, and as I mentioned in the previous examples, 0 factorial by definition is 1. So just a couple of examples to show working with factorials. We want to show that this is true. So since the numbers are a reasonable size, you could use your calculator to verify that the right side is equal to the left side. But I'm just going to use a more analytical approach, and the way I'm going to do this is I'm going to write the 5 factorial as 5 times 4, And then I know it's times 3 times 2 times 1, but the 3 times 2 times 1 I'm just going to write as 3 factorial. And the right side. Now I'm kind of doing a proof here, so I'm just going to put a line. And on the left side I can see that I have a common factor of 3 factorial, which I can factor out. And that would leave me on the front with 5 times 4. And factoring out 3 factorial leaves me with a 1. And so I have 19 times 3 factorial, which does equal the right side. Now I know these numbers are relatively small, so you say, well, why don't I just use a calculator to verify them? The process I've just shown is useful if you were to have bigger factorials. Like 1,000 factorial, the calculator can only do factorials up to a certain point, and after that we need to work more analytically. And a good example of that is this question here. NP2 equals 42. So I know by my formula for NP2 that would be n factorial divided by n minus 2 factorial, and that's going to equal 42. Now, to work the left side out, I am going to have to work algebraically here since I don't know what n is. So I know that by definition n factorial is n times n minus 1 times n minus 2 times n minus 3, etc., etc. But I'm just going to write n minus 2 factorial to represent everything from n minus 2 downwards, divided by n minus 2 factorial. And I think you can probably see why I did that, because I can see that these are going to cancel out. And so I'm going to have n times n minus 1 is equal to 42. So working this out, setting it to 0 since it's quadratic, I'm going to factor it. N could be 7 or n could be negative 6. Well, n can't be a negative value because we're talking about items, permutations, so that's rejected. So according to this, 7p2 is 42, and you can check that out on your calculator to see if that's the case. Should be. And here's one more example working with factorial notation. I want to simplify this expression. So n plus 2 factorial means that my first number is n plus 2, and then we go down one number at a time, 1 less than that, times 1 less than that, times 1 less than that, times 1 less than that, all the way down to 3 times 2 times 1, divided by, and n minus 1 factorial, again we start at n minus 1, and we go down by one number, multiplying, times n minus 2, times n minus 3, all the way down to 3 times 2 times 1. And in terms of simplifying, since I have factors in the numerator and denominator, common factors all reduce. All of this down to 1 is going to cancel out. And so I'm going to be left with n times n plus 1 times n plus 2. This is equivalent to this expression.